All right. Hi. Happy Thursday. Thank you for coming. It's our second to last Thursday of the semester. Hooray, we've made it. And we've got this class and the following class to do some instruction. And then next Thursday, so a week from today, will be project presentations. So remember that, keep that in mind. I have a note for this in order. So the STEM Center is kind of winding down for the semester. We've got STEM Center tutors. So there's no tutoring on Sunday, but Monday through Thursday of next week, there is evening tutoring. So if we have tutors for this class, so if you need to go talk to them, then 5 to 8 p.m., that's kind of where that is. Otherwise, if you need space to study or work, then you can always go there. So continue to work on your project. The minimal working example is due tomorrow. I know at least one group has already submitted it, and I have gone through and graded it how I would grade the final version. So I'm not expecting for this to be completely done. If you submit it, I will go through and check the rubric of these are the grades that you would get, but then you'll get full points for turning it in. So have something, and then that will help as you work towards the presentation. Okay, so for course evaluations, let me pause. All right, I have a quick announcement. So next Wednesday, I usually have office hours 10 to 12 on Wednesdays. But the math capstone presentations are going on at that same time, like right in the middle of it. So I'll be there for sure, 10 to 10:30, and then probably 11:30 to 12. Otherwise, I'm generally free, so you can always book an appointment during that time or outside that time, and I'm happy to talk about whatever. Okay, so for today, we're talking about algorithms. So we've kind of finished with recursion for now, and we're moving on to a new topic. So hopefully you're working on lab 8 and getting it done by tonight. All right. Okay. So now we get to talk about algorithms. So algorithm is basically something that lets you do something, right? So for example, if you have a recipe and you follow the recipe to produce, I don't know, chocolate chip cookies or a cake or something, you've been following an algorithm where the recipe says mix together the flour and sugar and baking soda or whatever and put the chocolate chips in and the eggs and what have you. And eventually you mix it all together, you put it on the pan, put it in the oven, and you take out your delicious cookies. That's an algorithm. So an algorithm is just a set of steps that you follow with some input and some output to produce a result. That's an algorithm. And so we've seen some algorithms before. So like you're writing in lab 8, you're writing recursive algorithms to get something done. And so to calculate whether something is a palindrome, you have your input as the word and the output being yes or no, this is a palindrome. So one of the ways we like to demonstrate palindromes is with like a box. And so you have some input, and then in here are some steps that are followed and output. So that's what we're working with.
Which one was this?
We're in the Unit 6 algorithms module, I believe. So with that of what is an algorithm, we need some way to keep track of how good of a job it's doing. And so with that, we use something called algorithm analysis. If you go on to take 374, we'll go into this in more detail. But algorithm analysis, we use it in order to measure the space and time that an algorithm is going to use. Because we saw with Fibonacci that some things are faster than others, right? If I give it fib of 5, it takes like no time at all. But if I give it fib of 50 or even fib of 500, with just the naive implementation, that's going to take forever, right? So there has to be a way to express that and say, this algorithm is worse than this algorithm. And so that's why we need this. I will also note that because the execution time, depending on which machine you're using, can be different. So like if I'm on this computer, which is reasonably fast, it's only a couple of years old, then it might not take a very long time. But if I pull out like my computer from 10, 20 years ago from my closet, it's going to be really slow. So, and that kind of idea where even compared with my computer to a supercomputer will probably do things a lot faster. So the time that it takes to execute can vary. And so that's why we need some sort of objective measure. We need a way to say, in general, this algorithm does well or does not do well. We need a way to express that. And that's where big O notation comes in. So if you look at algorithms on the internet, you'll see something like O of whatever. This is big O notation. And so this tracks something that we call computational complexity instead of the amount of time taken. So this is not, I'm running this on this one computer and clicking a stopwatch when it starts and clicking it when it's done. That's not what we're looking at. We're looking at what's the complexity of this in general. And so the way that we do that is typically in terms of n, which is the size of our input. So this is what you'll see typically, where n is whatever your input size is. Because typically when you have input to an algorithm, if you need to go through everything, then we write it in terms of n. We just express that variable. The basics for big O are essentially to choose the really important operation or multiple operations, and then count how many times that happens. So maybe your operation is assignments, or maybe it's something like adding, or in a linked list, for example, when we have the algorithm to go through the list to find a node, so like for get node, then maybe get next is our main operation. So that has to be something that you as the programmer, when you're looking at code that you write, you say, what's the really important thing that I'm doing here? And that's your operation. And then you count how many times that happens. So the easy way to do that is to look at the number of loops. So typically, if a loop goes from like 0 to n or n minus 1, and we do that operation, we count how many times that happens, and the number of times it happens would be n, because we're starting at 0 and we're looking at each thing up to n. So we can count that, because that's, yeah. So if we had some plus equals and that was our operation, then this would happen, since it's in terms of n, it would happen n times. Make sure you look at the arguments when you do this, because it's not always as simple. So sometimes we don't go from 0 to n minus 1. So make sure to read carefully. In general, there's also a tendency, so you end up writing some sort of equation. So let's say I do this 3 times before my for loop, and I do it twice afterwards. The number of times I do this plus equals operation is going to be 3 plus n in the for loop plus 2 down here. And so then I can write an equation to say that the time it takes in terms of n to do this is n plus 5. So typically you'll see like t of n equals n plus 5. And then what we do to get the big O notation is you ignore the constants. So 5 is a constant, get it out of here. Or if we had like 3 sets of for loops doing the same thing, this would give us 3 times n, because we're doing n 3 times, or n plus n plus n. So if we're reading on the same level, then it's addition. But if it's inside the loop, it's multiplication, because of the question is, how many times are we doing this? So if we get to something where we have like 3n, we ignore the 3 and we just care about n. And yeah, and so round up as needed as well. So that's kind of in general how to do it. We have examples that we'll go through in order to show you kind of the main categories of complexity. It ranges from all the way down near 1 to n or n log n squared, 2 to the n, or n factorial. And so you'll see, so like log n and O of 1, this is what we call constant time, because it basically happens in no time at all. It's not in terms of the input in any way. So those are really, really good. We like those. O of n is fair. O of n log n is, we're kind of getting where if we graph these functions, we can see this is the number of elements and this is the number of operations, or how many times we're doing this. And as these functions get bigger, like n squared is really bad, 2 to the n and n factorial are basically impossible. And I should have brought it in here, but there's a chart that says, actually, no, let me find that chart. Here it is. So there's a chart that says, here's the different sizes of input. And so if the algorithm is a log n or n log n running time, how long does it take us to do this algorithm on like a million or billion size input? And so you see that log n, and n log n for really big inputs are like fairly okay. All of them up to n squared kind of do really good with small amounts of data. But once it gets bigger, then we're up to like 31 years for this algorithm to finish, which is not good. And then when you get into this kind of exponential or factorial running time, then it's like anything bigger than 10 for n factorial is no good. Yeah, so this is why, like, this chart is kind of why we classify those in that way. Just because n squared, 2 to the n, and n factorial, they grow really quickly. And so we don't want to write algorithms that have those behaviors. Where'd it go? There it goes. Okay, so I'm going to give you some examples. So let's say we're going through a phone book. So an example for a constant time algorithm is, let's say I know the page number and I know the name that I'm looking for. So I know not only what I'm looking for, but also where it is. And so I just open the phone book to that page and then find the name. A log n algorithm is binary search, like what we talked about last time, where you know the name that you want to look for, so you open it halfway through and you ask, are we there yet? And then if we're not there yet, then we go to the left half of the book. Or if we went too far, then no. If we went too far, we go to the left half. If we went not far enough, we go to the right half. And so that's binary search, and that just repeats. That's log n. O of n, which we just call linear. That's, let's say we have a phone number and we want to find who it belongs to, but we don't know the name or anything. So in that case, we would need to go through every entry in the phone book to find, does this phone number match? That's linear search. For n log n, this is like if we had all the pages that were in random order, we wanted to take a page and put it in its proper place in the new book. So we can, like, if we go through all of the pages, we have to go through all the pages. That's why we have n. And then log n is we're putting it in the new book in order. And so this part is just the binary search again. So once we have a page to put in, we do binary search on what we've got so far and then put it in the correct place. And then for the n squared and other worse algorithms, let's say we have a stack of phone books and we've got our, was it like the whiteout? We need to go through and fix a typo for every entry. So we have to go, in the first phone book, we have to go through each entry and make the corrections. And then we have to do that for every phone book. And so since we're going through each entry in the phone book n times, then that's a quadratic function. And then n times n factorial, this is like one of my favorite algorithms, which is just Bogosort, which is, it's a sorting algorithm that is famously terrible, where the way that we figure out that the way that we sort it is you check if it's sorted, and if it's not, you shuffle it, and then you check if it's sorted, and then you shuffle it, and then you check if it's sorted. It's absurdly terrible. Yeah.
Kind of like off-topic question.
Okay.
So I asked ChatGPT if GPUs can like accelerate like time complexity for like algorithms, and it said not time complexity but runtime.
Mm-hmm.
What's the difference between the time complexity and runtime of an algorithm?
Yeah, so the runtime is like the stopwatch of I'm starting this algorithm, set the timer, and then it's done and you click it again. That's going to vary depending on your hardware.
Okay.
So like your computer versus, I think classroom computers are fairly slow, or like your parents' old computer that they have in the basement is going to be very slow. But the time complexity is this generalized way of looking at an algorithm, where if we know the input and we write it in terms of n, that's like, it's machine independent. Right. So if we have some time complexity that is not good, we need to write a better algorithm. And there's nothing that a computer can do to make that faster. Okay. I have to tell you about logarithms because people tend to forget. It's also been a long time since I studied logarithms, but you'll see like log n or n log n in algorithms a lot. And if you remember from like pre-calculus or something like that, where you typically have like log base 10 or log base 2, if you remember, there's a formula for that. I think I have it in the other presentation as well. I do. No, this is it. Yeah, so we use logs when we're dividing something. So typically, if we're dividing the input at some point, then we use logs. And the amount by which we divide, that gives us the base of the log. So generally, like binary search, where we divide it in half every time we go around, then that's log base 2. Or if we're dividing it by 10 every time, then we get log base 10. But typically, we as computer scientists looking at big O notation tend to be like, nah, we're dividing, just don't care about the base. So you'll see once we write in O of log n, once we decide the biggest term in this whole equation that we write, then the big O doesn't care about the base at all. Okay, so let me walk you through this worksheet. Let me pause and pull that up. Okay, so this is a worksheet that I have. I've got copies of this I'll hand out. And so your job for each of these is to go through and for each of these, I've given you a bunch of algorithms. Some of them are in Java, some of them aren't in Java. And your job is to read them and say, what's the complexity of this? So let's take the very first one and we'll do that one together. So first we look at this and we ask, what is the main operation? If we look at this, there's some addition, there's some assignments. So I might say that assignments is the operation. So the operation is equals. And then now I ask, how many times does it happen? So it happens once here, once here. How many times does it happen here? So we do a plus random, but since it's for I in range n, we do this n times. So this happens n times. And then here for the assignment, we do this m times. And so once we go through, we have our whole equation. So we can write T of n, typically we do capital T, equals n plus m, and then you can tag on the constants at the end, plus 2. And then to get the big O notation, you round up, ignore the constants, so you get O of n plus m. So that's how we get that. So we have some longer equation, and then from that, we ignore things, round up, and get our final big O of n plus m. So I have a lot of equations for you to try that out on. And then on the back side of that, I have a bunch of equations. And so your job here is to first we need to find what's the biggest term. That's how we decide big O. So we've got all of this. We've got 0.001 n cubed plus 0.25 n. And the question here is the n cubed term bigger than the n term? So here's the point where like when I say ignore constants, this is one of the places where this comes up. Where even though we saw let's go back to the chart. Went too far. Like we see this chart. And so even if the modifier on n squared, or is it n cubed? N cubed, even though the modifier is a lot smaller than it is on n, because it's cubed, it's going to grow a whole heck of a lot faster than n once the input gets big enough. So for that, we say that the dominant term is 0.001 n cubed. And so from that, once we've found here's the biggest term in this equation, then we say this is O of n cubed. So it's teasing out this process where we have an equation. So find what's the biggest term. You can plug it into a calculator or Desmos. You can like plot the different terms and see what comes up, what's bigger. And then write O of, throw away any constants and just write it O of like n cubed. And then from there, have two additional questions of the big O of some algorithm is this. And if it takes this many seconds with this amount of input, how long does it take for this amount of input? So this is going to be just algebra. So take a stab at this, and if we've got questions, then I'm happy to go over it. So my plan is to maybe spend the next, let's say until like 4:10 or so. So maybe like 10 minutes working on this. Any questions, clarifying questions before we start? Points of confusion? All right. Okay. So we've got that one. Let's look at this one. So what's our operation? We could go for assignments again. We could go for some other arithmetic. Let's keep it consistent and do assignments. So here, depending on how you count, it's maybe 1 or it's 3, because we're assigning 0 to 3 different variables. And then here, we start at 2 and go up to n, but we increase by a factor of 2 each time. And then in here, we're doing something where we divide n by 2. And here we also start at n over 2, and then we go until it's less than n. And we start at halfway through, and then we increase it. Any ideas? N over 2 squared. Okay, that's a fair idea. Okay.
What's the operation in this?
Let's say assignments. Okay, so let me tell you the answer. So this outer for loop, we start at n but at a half. And then we go up to n. So in that case, we end up doing this n over 2 times, right? Since we start at half and work our way up. This is actually an example of a log where because we're dividing n, this gives us the log. And so it's, since we're starting at 2 and going up to n, maybe it's log base 2 of n. And so when we go to write our big O, we have n over 2, maybe a 1 at the beginning.
So what's the T?
I think it's probably this. Or n over 2 times log base 2 of n.
Right.
And so what happens here is we get rid of the constants. So the biggest term is n over 2 times log base 2 of n. So we get rid of the constants, so that takes care of the 1/2. So we just write n. Then we get rid of the log base, and so we just write log n. And that says that this one is n log n. Okay. Let's do an easier one. Let's tackle this one. Wait, is that the easy one? Yeah, close enough. Actually, let's do this one, and then we'll move on. Because we've got sorting to get to today as well. So let's take is prime. So in terms of n, this kind of if statements take
What is our operation?
our operation. What do you think it should be? Returns. So returns only happen once in a function. I don't know. Maybe it's this evaluation of the if statements, or this testing if it's equal. Maybe equals equals. Or testing like some logic Boolean operation. So maybe our operation is Boolean. And so here we're evaluating some Booleans, and that just happens once. But here in the for loop, we're evaluating this how many times? And -2, because we start at 2. So that gives our T of n to be 1 plus n minus 2, which is n minus 1. And so this gives us a big O of
N?
just n. Yeah. Okay. Let me just tell you what the answers are for the rest of them. And then I will let you go home and figure it out. Okay, so this one ends up being, we do the outer loop. So in terms of how many times we're doing the inner loop, first we do it, so So while j is greater than I, we work all the way down. So the first time we'll do this inner loop n times. And then we'll do this inner loop n minus 1 times, right? Because I moves up to 1. And then n minus 2 times. And then n minus 3 times. All the way down. And so there's a fancy mathematical equation for this, where this is do you remember the sum of n numbers? 1 plus 2. Yeah. And so we know the equation for this. It's n times n. Is it plus or minus? I think it's minus 1 over 2. Thanks, calculus. And then if we expand this out, this gives us, was it n squared minus n over 2? And so we choose the highest term and ignore everything else, and this gives us O of n squared. This one actually ends up being a case of log base 2 of n, which is just O of log n. Let me see what this one is. Oh, wait, I have. I don't know, where is it? This is also, so here, since we're multiplying by k each time, it is log base k. And then when we write it, it's log n. This one, value, and this one is O of n squared. We did that one. We did factorial. We did that one. Okay. And so I'll post this document again. And lucky for us, we've got one more chance on Tuesday to take another stab at this. Can we go down the sheet and someone just tell me what their big O is for each one of them? Just call it, just, okay, yeah, if you got some of them, then tell me what they are. Just call it out.
I didn't feel I didn't see the one. I didn't see one of them.
Oh, that's okay. So yeah, so just whatever you did on this side of the sheet, that's fine. But I would like to know what your answers were for the other side of the sheet. So just call it out, whatever you got for the second one. Any ideas? What about the next one?
O to the n to the 1.75.
Because 1.75 is bigger than 1.5. And these numbers for the exponents, you don't round up because there's a significant difference in the efficiency of an algorithm that is to the 1.75 instead of 2. Like there's a famous algorithm where if everybody thought it was n squared and then someone reduces it even by a little bit, then hooray, we did a little bit better. All right, what about this one? N squared log 2n or n log 2n squared. This one I think was tricky. the answer here ends up being, because we've got an n squared out there, it ends up being O of n squared log n. Okay. What about this one? 100n versus 0.01n squared. Ideas?
103.
Yeah,
That's 100
100n.
It was 0.01 squared.
Yeah. Because the thing is, because n squared will grow so much faster than 100n, even though like this is 100 times, wait, no, 1,000? Yeah, so this one grows a whole lot bigger. So we ignore the constant and say n squared. Okay. So I'm just gonna,
Wait, what was it for the n plus 0.01 and 2?
n squared.
Oh.
Okay, so I'll kind of walk you through these ones. So for this first one, the big O of a particular algorithm is n cubed. And so it takes 2 seconds to complete the algorithm with 1,000 inputs. So we've cubed the inputs. And how long would it take with 10,000 inputs? So since we want to know the amount of seconds, we have 2 equals 1,000 cubed, but there's some overhead time involved in doing the processing. And so we want to know for this particular machine, how, like, what's that overhead factor? Where we can take our input size and cube it, but then it's going to take the computer a certain amount of time to do that work as well. And so to get that, we have 2 over 1,000 cubed, which I will tell you is, this gets evaluated to, this is 10, or sorry, this is 1 times 10 to the 9th. And so if we divide that by 2, it gets to be 2 times 10 to the negative 9. Bring back scientific notation.
Wait. 2 times.
Negative 9. And this is the amount of time of seconds of overhead per input. So for each one of n, there's some amount of time that it takes to process that on this particular machine. And so now that we know this number, we want to know how many seconds it takes to process this with 10,000 inputs. So we cube that, and then we bring in our 2 times 10 to the negative 9. And we do that, we do the math, and that turns out to be 2,000 seconds. Okay, I'll tell you the answer for the other one. The other one is 16. So if you go home and you work on this and you do that same format, you should get 16. Okay. This was hard. Yeah, it's hard bringing math back into it, but we need these skills in order to say, here's how good our algorithms are. So especially if you go and take 374, there's a lot more of this. Yeah. So with that, let me think. So I think for active learning, you can keep this if you want to take it home and finish it and convince yourself that these are the answers. I'll post these answers on Canvas. I'll post them in the,
What we supposed to turn in for active learning?
nothing for active learning.
Okay.
But I want to at least get started on sorting. Because we need to know here are some sorting algorithms. Okay. So once we know how to measure efficiency, now we transition to some of the more high level computer science topics. So once you learn, here are some common, like first you learn how to code, and then you learn here is some common data structures. So here is how we can use code to store data. And so that's our inheritance and our linked list stacks and queues. And then now we talk about efficiency of how good is this thing that we're writing. And so we're going to look at some common algorithms, which are sorting. And the reason we talk about sorting is because it's really important in all sorts of applications to have things in order. And so we want to be able to figure out a way to sort something. So what I think I'm going to do is, without having watched this video, I'm going to hand out some cards, and I want you to work with a neighbor and ask, I'm going to give you like a suite of cards, and you're going to ask, how do I sort this? So if it's all shuffled, how do I put it in order without learning any of these algorithms yet? Because I think this is always really interesting to see what you do before you know. Okay, so you look for the smallest thing, take that out every time, and then build up the deck like that. Okay. Anybody else have a way that they do it? Yeah.
For the, like, I kind of went by so, I think I started at the second card, and then I checked if it's greater than, or sorry, no, sorry. I checked if it was like less than the previous one, and if it was, then I like moved it until like there's no cards like before it, and then I just like repeated that.
Move it left to correct spot. Okay, anybody else? Yeah.
Kind of narrowed it down to having three options, either the minimum of the list, the maximum of the list, or between two values. So just keep going through each card, check if it's either the min, max, or find the two cards it's between.
Ask if, so for each card you ask if it's minimum or maximum or otherwise.
Else, find the two cards it's between.
Find the two it's between and then put it there?
Yeah.
Okay, that's interesting. I haven't thought of that. What else do you have? What other ways do you sort this thing? Do one more.
That's part of sorting like this or like this.
Like looking at it.
Oh.
Because you want to put it in order. So you have to look at like what's the value of the card in order to sort it. Go for it.
Well, are we trying to find this like any method or?
Yeah, I'm wondering, what do you do to sort? What do
find
you?
it? You could randomly shuffle the deck until it's in perfect order.
Infinite Machi theorem.
Yeah, you could do BOGO sort. Which is just shuffle it. Is it sorted? No, shuffle it. I might, man, I forgot about it this semester. I have an assignment that is called Worse Than BOGO Sort, which is to write me a sorting method that's worse than BOGO sort.
It takes even longer.
Yes. And that's a fun one. I might have that for the last week of class. If you want extra credit, write me a method that's worse than BOGO sort. Okay. So thank you for indulging me. Let's see, this video is 4 minutes long, which means we've got enough time. So this is the video that I like to use to introduce sorting. So I'll pause recording and then we'll watch it. Okay. So I really like that video because I think it visualizes it well. Of these are the different sorting algorithms. So I will say that that's insertion sort, where we start at the second thing and then we move it along until we get there. This is insertion sort. This actually ends up being something we call selection sort. I unfortunately don't know if this is any named sorting algorithm. Chances are it might be. But the ones that you've named are actually well-known algorithms. Okay, so we're running out of time. So here I have homework for you. There's a set of videos that I'm going to show you that I'm going to send to you for you to watch and learn. Here's how these different sorting algorithms work. Because algorithms are kind of our box, we have some array full of things that are maybe unsorted. And then as a result, they're all sorted at the endpoints. They just have they have increasing levels of, like it starts off really slow and then it goes to really quickly. So these end up being n log n, where bubble sort is n squared. So we kind of study them worst to best. So I'm going to send you a list of videos. I would like you to watch the videos before class on Tuesday, where on Tuesday we'll kind of go over them. We'll probably have some time to work it out with the cards. And then we'll do lab 9 on Tuesday as well, which is sorting. And that is, I ask you, here's the different situations, which algorithm do we choose? So you have to know how these work generally before you come to class on Tuesday. Sounds good? Okay.
Where do we access the videos?
So first of all, you can access the videos in the slideshow because the slideshow is posted on Canvas. But I will send out an announcement with a list of all the links. Okay, thank you. See you Thursday. No, today's Thursday. See you Tuesday.